Okay. In this unit, we are going to start looking at derivatives, and derivatives give us the instantaneous rate of change of something. So the first thing that we're going to start off talking about today is the average rate of change versus the instantaneous rate of change. An average rate of change is something that we already know how to find, whereas instantaneous rate of change requires some knowledge of calculus to be able to determine. So here we have, we're going to look at a few average rate of change problems first. And here we have Jennifer. She is traveling north on I-77. She passes mile marker 9, so she's at mile marker 9. She's down around Charlotte at 5:22 p.m. She passes mile marker 73 at 6:33 p.m. What was Jennifer's average speed in miles per hour from mile marker 9 to mile marker 73? So if we're looking at this problem, we know that the average speed is distance over time. So we need to find her distance. So to find her distance, we know she goes from 9 to 73. So if we do 73 minus 9, we are going to get 64 miles. We also need to know the amount of time that she took here. So we've got from 6:33, we're subtracting 5:22. That is going to give us 1 hour and 11 minutes. But of course, whenever we want to know miles per hour, we can't put in hours and minutes. So let's convert those minutes to hours, and we can do that really easily just by doing 11 divided by 60, which is going to give us 0.183 repeating. So this is actually 1.183 repeating hours, and this is miles. So if we divide those two, 64 divided by 1.183 repeating is going to give us approximately 54.085 miles per hour. So Jennifer's average speed is around 54 miles per hour. Now, if you think of the situation, it makes sense. She is in Charlotte at 5:22 p.m. and many of us have probably been in Charlotte traffic around 5 o'clock, and you're probably going slow. So by the time she gets to 73, she's probably going a lot faster. But her average rate of speed is slowed down because she probably sat in some traffic near Charlotte at that time of day. So this is average rate of speed. One thing I want you to notice here is that this 73 minus 9 over 633 minus 522, this is a slope formula, because if we think of this with our x being our time and our y being our distance, then we have found the slope between the 2 points on the graph here. So let's look at another problem. Okay, this time we have a table. So we could, if we want, graph these points as well. This function gives the number of students who have voted for homecoming queen as a function of time, t. Time is measured in hours since 8 a.m. on the day of voting. What is the average rate of change of f of t on the interval from 0 to 4? Explain this rate of change in context of the situation. So here, we want to know from 0 to 4. Be careful with this because 4 is right here. We're actually not using that last point. And so whenever we think about the rate of change is slope. So we're looking at the point 0, 35, and then also the point 4, 256. And so if we're finding the slope of this, we know slope is y2 minus y1 over x2 minus x1. So we would do 256 minus 35 divided by 4 minus 0. 256 minus 35 is going to give us 221. And that will be divided by 4, and 221 divided by 4 is 55.24. And so we have 55.24 what? So whenever we're thinking of this, this is hours here, and this is votes right here. So if we want to explain this, we were doing change in Y, which is votes, per time, which is hours. So if we want to explain this, we could say that from, I'm going to say 8 a.m. until 12 p.m. So from 8 a.m. until noon, because those are the first 4 hours, students voted at a rate of about 55.24 votes. That should be a 5. I don't know why I wrote a 4 right there. It should be a 5. So 5 votes per hour there. And so this is an average rate of change. It might be that, like right here in the morning, we really didn't have that many votes. You see a lot more votes shooting up here in the from 2 to 4 hours right here. So this is our average for that time period. Okay, now let's look at what happens if we want average rate of change just for a function. So here we have the equation f of x equals x minus 2 squared plus 1. And so we want to know on the interval from -1 to 3. And if we want to know that on the interval from -1 to 3, what we need is the slope between the endpoints. So what we need to find first here is we need to find the coordinates of those endpoints. So if I find f of -1, then at -1 I would have -1 minus 2 squared plus 1, which is going to be -3 squared plus 1. So 9 plus 1 is going to give us 10 for our f of -1. Then we also need to find f of 3. So if we find f of 3, that is going to give us 3 minus 2 squared plus 1, which is 1 squared plus 1. So we're going to get 2. So we have the point -1, 10 is on the graph. We also have the point 3, 2 is on the graph. So I've got a Desmos that we're going to look at here. Get rid of that so we can see it. So this is our graph here that we're looking at. And right here at -1, here's our point -1, 10. And right here is our point at 3, 2. And so what we want to know is the average rate of change. So that's going to fall upon this line right here. And we need to know the slope of this line. So let's go back. We've got our 2 points. If we want to know the points of that line, we just need to do 10 minus 2 over -1 minus 3. So we're going to get 8 divided by -4, which is -2. So that average rate of change of that graph from -1 to 3 is going to be -2. Okay, so let's switch from average rates of change to instantaneous rates of change. So I'm going to bring up this other Desmos graph here. Maybe if it'll go, there it is. Okay. All right, so what I have here is I have a graph of a rational function. The equation of this rational function is over here. It's f of x equals the square root of x plus 7 over x minus 3. It really doesn't matter that much what that graph is. We could do this with any graph, really, as long as it's continuous at the points we're looking at. And so I've got these 2 points here. I've got a point x, f of x, and I got this other point a, f of a. And so you can see right here, I've got the slope between these lines. So let's say that I want to know the rate of change of this graph at this point right here, this purple point a, f of a. And so if I want to know the instantaneous rate of change at that point, I could estimate this by finding an average rate of change. Maybe I could find the slope between these points. But then it'd be a little bit better if I moved this point a little bit closer. Finding the slope between these 2 points would be even better. But if I move x a little bit closer, then it would be even better. See how close we're getting here to having that slope at that line. And then a little bit closer, and a little bit closer, and a little bit closer. If I could actually get x right there at a, it actually disappears because of the setup of this graph. But if I get really, 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 really close to a, you can see that this looks like a tangent line right here. A tangent line is a line that just touches that graph at one point, and that slope is going to be our instantaneous rate of change if we can get all the way to a. Now, I should be using some language here that makes you think a little bit of limits, because I was saying that x is getting closer and closer and closer and closer and closer to a, which we could also think of as x approaches a. So you should start to think in terms of limits a little bit here. And so the closer we get to a, the closer we get to that instantaneous rate of change. So let's go back to our notes, and I'm going to give you a really important definition here, and that is the limit definition of a derivative at a point. So for this limit definition, we are going to have the limit as x approaches a. So a is the point that you're looking at here, of f of x minus f of a over x minus a. And you may be thinking, where does that come from? Well, if I have 2 points, I've got x and f of x. And then I also have the point a, f of a. And notice if I do slope formula with this, then y2 minus y1, f of x minus f of a over x minus a. You could actually interchange which one comes first, but typically you see it written this way first. So this is our limit definition of derivative at a point. So let's look at a problem that is going to ask us to use this. All right, so we're going to look at one of these at a specific point, and we have the instantaneous rate of change of f of x equals the square root of x plus 1 at t equals 3. That should say x equals 3. Let's fix that. So let's look at the graph of this just to get a picture of what's happening here. And so if we look at this graph here, this red graph right here is our function that we're looking at. It's the square root of x plus 1. And we've got this point right here on the graph. This is at 3 f of 3, or specifically it's going to be 3, 2, which we'll find here in a second. And if I have this point here, oh, I should have labeled, hold on, let me change this really quickly. Let's label this x, f of x. So if I take this point right here and I move it closer and closer and closer and closer to that point 3, I get closer and closer and closer to having a tangent line there, a line that just touches that curve right there at one tiny, tiny point. So you can see that x is approaching the value 3 here. X is getting closer and closer and closer to 3. So let's set this up. All right, so our limit definition of the derivative tells us that we're going to do the limit as x approaches a of f of x minus f of a all over x minus a. Essentially, it's just the slope formula. Our a in this case is going to be our 3. So what we're finding is the limit as x approaches 3 of f of x minus f of 3 all over x minus 3. And so we can find f of 3. We just have to plug in a 3 into our formula. So f of 3 is going to be the square root of x, 3 plus 1, which is going to give us the square root of 4, which is 2. So we know that this value right here, that f of 3, is 2. So we could replace it. We also have f of x here. Well, f of x equals this equation square root of x plus 1. So the other thing that we can do here in this next step is we can replace f of x with what f of x is equal to, square root of x plus 1. And we can replace f of 3 with 2. The other way to think of this is that your one point that you're looking at is the point 3, 2. Your other point is x, f of x, but we said f of x is square root of x plus 1. So these are the 2 points that you're using, and you're doing slope formula with these. So square root of x plus 1 minus 2 over x minus 3. That'll get you straight to here if you want to skip those first things that I wrote down. And of course, we're looking at this limit as x gets closer and closer and closer and closer to 3. So here we have our limit set up. And once we have our limit set up, we're just going to use some of the rules that we used whenever we were solving limits to find the answer here. So we're going to have to multiply by the conjugate. And the conjugate for this would be square root of x plus 1 plus 2. And we must multiply in the numerator and denominator for these. So when we distribute here, we're going to have x plus 1, and then we'll get a plus 2 times the square root of x plus 1 and a minus 2 times the square root of x plus 1. Those values are going to cancel out, and then we'll have minus 4 over x minus 3, and this needs some parentheses around it, times the square root of x plus 1 plus 2 here. And of course, x plus 1 minus 4 is x minus 3. So we've got the limit as x approaches 3 of x minus 3 over x minus 3 times the square root of x plus 1 plus 2. Our x minus 3's here will cancel. And at this point, we can plug in our 3. So we are going to get 1 over the square root of 3 plus 1 plus 2, which is 1 over the square root of 4 plus 2, which is 1 over 2 plus 2, so we get 1/4 as our answer here. If I go back to that graph really quickly, we can see here, if I try to get, I can't get exactly at that point, but if I get really close to the point, you can see it looks like that's about right, because our slope is about 1 over 4, up 1 over 4 here. So that is our instantaneous rate of change at that point. Let's try another one. So this time the position of the particle is moving along the x-axis. It's given by this equation, x plus 1 squared. What is the velocity of the particle at t equals 1? So here our equation gives us position. We can also think of that as distance from the origin. And so our equation here is, we've got, well, they don't say t is time, but we've got time right here on the x-axis. And then we've got position or distance from the origin right here on the y-axis. So if we want to know velocity, which is distance over time, then we need to find the slope, because that'd be change in y, which is distance over change in x, which is time. So we need to find the slope. So we're looking at finding a slope here. We're going to use the limit definition of a derivative. So again, I'm going to write it down just so we've got it. Limit as x approaches a of f of x minus f of a over x minus a. And here our a is 1. So we will be doing the limit as x approaches 1. And I'm going to go ahead here for f of x. I'm going to use x plus 1 squared. And f of a, let's just go ahead and find f of 1 up here. It would be 1 plus 1 squared, which is going to give us 2 squared, which of course is 4. So I'm going to put minus 4 over x minus 1, because 1 is my a value. So for this one, I need to expand a little bit here. So whenever I expand x plus 1 squared, I can square double square there. So that will look like this. X squared plus 2x plus 1 minus 4 over x minus 1, which is going to give us the limit as x approaches 1 of x squared plus 2x minus 3 over x minus 1. And I believe that x squared plus 2x minus 3 is going to factor for us. It'll factor into x plus 3 x minus 1. Conveniently, we've got an x minus 1 in the numerator and denominator here. And so those will cancel. We can plug in our 1, and so we get 1 plus 3, which is going to give us 4. So our answer for this question is 4. The rate of change here, or our velocity, would be 4. Okay, here is our last question that we're going to look at, and it says, given the function f of x equals 1 over x, we are supposed to find, and here's some new notation for you. You've got f with this little tick mark behind it, and a parentheses -1. And so f with that little tick mark behind it says the derivative of f. And remember, at the beginning of these notes, I said we will be talking about derivatives. Derivatives give us the rate of change. So we're looking at the rate of change of f at -1 is what we're looking for here. So we would be using that limit definition of a derivative. So for this one, we would have the limit as x approaches -1 of f of x, which is 1 over x, minus f of -1. So if we plug in -1 here, f of -1 is going to be -1 all over x minus -1. And so we end up with the limit as x approaches -1 of 1 over x plus 1 over x plus 1. The easiest thing to do here to simplify this is if you just multiply the numerator by x and the denominator by x. If we distribute here, x times 1 over x is just going to be 1, and x times 1 is x. And then in the denominator, I'm not going to distribute because I want things to factor and cancel. And if you see here, you've got this x 1 plus x. That's the same as x plus 1, so it can cancel here. And we're going to get 1 over -1 when we plug in our -1. So we get -1 for our answer. Okay. The next part asks us to find f prime of 1. So we're doing the same thing except for our a value is 1 here. So that's going to look like this. We'll have the limit as x approaches 1 of 1 over x, which is our f of x, minus the a value, which in this case is 1, over x minus the a value, which is 1. And so we can do the same thing here that we did on the last problem. If we multiply the top and the bottom by x, when we distribute, x times 1 over x is just 1. Let me write my limit notation here. It's very important. So we get 1 minus, and here we have an x, over, and I'm not going to distribute here in the denominator because I want something to cancel. Now, in the first problem that we did, the 1 plus x and the x plus 1 could cancel. They're equivalent. However, x minus 1 and 1 minus x are not equal to each other. So we cannot just cancel these right away. But what we can do is we can factor a negative 1 out of that numerator. And if we do that, we'll have our limit as x approaches 1 of negative 1 times negative 1 plus x over x times x minus 1. And whenever we do that, now you can see we could rewrite this. I'm showing every little step here. You might could skip this one right here. So I'd have negative x minus 1 over x times x minus 1. And so my x minus 1s will cancel here. And then I'm going to plug in my 1. So I'm going to have, that's going to be a negative 1 in the numerator over a positive 1. And I still get negative 1 for the answer for that one. Our last thing that they ask us to do is to find f prime of negative 2. So we're doing the same problem over again, but we've got to use that negative 2. So we're going to have the limit as x approaches negative 2 of f of x, which is 1 over x, minus f of negative 2, which is going to be 1 over negative 2 here, over x minus negative 2. And so what we've got is we have actually, let me not be so lazy. I need to write my limit notation. Limit as x approaches negative 2 of 1 over x plus 1 over 2 over x plus 2. And so for this one, since we have this fraction on the second part here, what we really want to multiply by here is our least common denominator. And so that would be a 2x. And so if we multiply 1 over x times 2x, that 2x is in the numerator, just the x's cancel, and we get 2 over 1, which is just 2. And if we multiply 1/2 times 2x, then the 2's can cancel, and we'll just have x there. So I get 2 plus x over 2x times x plus 2, and I'm going to be a really good calculus student, and I'm going to write my limit notation here. And so we can see 2 plus x and x plus 2 can cancel, and we are going to get 1 over 2 times our negative 2. So our answer for this one would be negative 1/4. Okay, so we did that same problem 3 times. That with different numbers, it becomes a little bit long to do the problem like that. In one of the upcoming sections, we are actually going to look at a way where we can figure out how to do that where we don't have to do the problem 3 different times. So there is another way that we can do that, but we are not going to do that just yet. So this is all I have for this section. You'll have an assignment that goes with it. If you have any questions, let me know.